2,300 years ago, this familiar sight, the first quarter moon, was central in a demonstration of the power of the human imagination. At that time, Greek philosopher Aristarchus was one of very few who understood the geometry of the solar system, that the Earth orbited the Sun and the Moon orbited the Earth. He knew that an eclipse occurred when the Moon passed through the shadow of the Earth. By comparing the eclipsed Moon to the size of the Earth's shadow, he was able to state that the Moon was approximately 1/3 the size of the Earth, a pretty good estimate. Then, using some basic trigonometry, he was able to estimate the distance to the Moon, a remarkable achievement. He then turned his mind to another problem, the Sun. The debate in 300 BC revolved around whether the Sun was a huge object at a considerable distance from the Earth, or a relatively small object sitting close to the Earth. Aristarchus resolved this debate. He realized that this first quarter moon revealed an important moment in the orbital relationship between the Earth, Moon, and Sun. At this moment, when we see half of the Moon illuminated, the angle between our line of sight and a line from the Sun to the Moon is 90 degrees, creating a triangle that looks like this. M represents the Moon, E and S the Earth and Sun. Aristarchus had determined EM, the distance to the Moon. If he could determine the angle E, he could solve this triangle and determine ES, the distance from the Earth to the Sun. Today it is March the 8th, 2014. The Moon is high in the southeast sky and is half illuminated, a first quarter moon. I will attempt to measure the angle E using equipment similar to what Aristarchus may have used. This is the device I'm planning to use. I mounted a plywood table on an old telescope mount. The table can be rotated to any orientation. I taped a piece of white card to the device. We will record the angle lines on this card. This rotating arm is first aligned with the Moon, and then with the Sun. This determines the angle between them. The table has to be oriented such that it is in the same plane as the Moon and Sun. That is, if we could extend this table into space, both the Moon and Sun would be sitting on it. It took a lot of trial and error to achieve this alignment. With the Moon aligned along one edge, I watched the shadow cast by the Sun until the table was aligned properly. If I built this device again, I would have one axis of rotation along the edge of the table, not in the middle. Once the table was oriented properly, I aligned the movable arm with the Moon. I used 2 vertical rings to help with alignment. With the arm in place, I drew a pencil line representing the Earth to Moon segment of the triangle. Rotating to the Sun gives us the angle between the Moon and the Sun. I watched the shadows from the rings to determine alignment with the Sun. Holding the arm in this position, I drew a line representing the Earth to Sun segment of the triangle. Now to solve the triangle. This is the card with the 2 lines. This is the Earth-Moon line, and this is the Earth-Sun line. Using a protractor, we determine the angle from the Moon to the Sun to be 89 degrees, very close to 90 degrees. Back to our triangle, we now know that angle E is 89 degrees. This triangle is distorted to fit on the page. The actual triangle is a long, thin triangle. With angle E determined, we can use some trigonometry to solve for the distance to the Sun. You may recall that the cosine of an angle in a right-angled triangle is the length of the adjacent side divided by the hypotenuse. In this case, the cosine of angle E equals EM over ES. We are trying to solve for ES, the distance to the Sun. Aristarchus used the distance from the Earth to the Moon as 1 unit of length. We will do the same. EM equals 1. Our equation looks like this. Rearranging, we get ES equals 1 divided by the cosine of 89 degrees. The cosine of 89 degrees is this. This rounds to 0.0175. Inserting 0.0175 into the equation and solving, we determine ES equals 57.3. According to these calculations, the Sun is 57.3 times the distance from the Earth to the Moon. This confirms that the Sun is located a great distance from the Earth. How do our results compare with those of Aristarchus? He measured angle E to be 87 degrees, and then calculated the distance of the Sun to be 20 times the Earth-Moon distance. Less than our results, but still placing the Sun at a much greater distance than the Moon. How do our results compare with current knowledge? It turns out that the Sun is located at 390 times the Earth-Moon distance. We were both off by significant amounts. The main source of error comes in attempting to measure the angle to the Sun using primitive equipment. Looking at the protractor, we can see that the pencil line itself represents almost 1 degree. Using modern knowledge, we know that the angle to the Sun at the moment of the first quarter moon is actually 89.85 degrees, less than the width of a pencil line difference from our measurement of 89 degrees. A tiny discrepancy in measuring creates a significant inaccuracy in the result. And there is also the issue of determining precisely when the first quarter moon occurs. Despite the difficulty he had in acquiring precise measurements, Aristarchus made a momentous contribution to early human knowledge. He placed the Sun, Moon, and Earth in order. The inspiring aspect of the accomplishments of these early philosophers is what it reveals about the power of the human imagination, to be able to look at a puzzling and complex structure like our solar system and reveal its architecture. You can find more about these great minds at our website, hylaroad.com. Follow the videos link.